Yes.
Okay, so the motion starts from a point A, then moves to a point B using the time dt. And here we usually consider small displacement. Okay, just a small displacement. So A to B using the time dt. And because it's a small displacement embarked by the body, that's why the time is dt, small t. Now you realize that the displacement of the body, so let's also represent the displacement from a point A to B to be ds. Because it's small, that's why we have ds, dt, and so on and so forth. Okay. Now, the observation is that the linear displacement within the circumference of the cycle, okay, also subtends a certain angle at the center. Linear displacement within the circumference of the circle subtends an angle theta at the center of the circle. Okay, now the greater the linear displacement, the greater will be this angle subtended at the center. So when the body moves from this point and then comes to a new position B, okay, we can trace the new position of the body to the center. And when we do that tracing, okay, we realize that this linear displacement is equivalent to this angle at the center theta. Okay, when the body moves from A to a new position C, okay, we can trace the new position of the body to the center of the circle. And when we trace that, this is it. Okay, and this is the whole angle connecting the new position of the body. The greater the displacement, the greater is the angle subtended at the center. When the body goes through half of the circumference, meaning it moving from this point to this point. Let's assume this is a point D. You realize that there's the whole distance or linear displacement within the circle. And then this is the whole angle corresponding to it. Okay, the greater the linear displacement within the circle, within the circumference, the greater will be the angle subtended at the center. And so we conclude that the linear displacement S, because this time it can be large, we are moving from ds to S. Okay, the linear displacement within the circumference S is directly proportional to the angle subtended at the center theta. Okay, and this angle is what we are calling as angular displacement. So theta is the angular displacement, whereas S is the linear displacement. So in circular motion, we realize that the linear displacement is directly proportional to the angular displacement. Please, are we okay? Hello, are you there?
Yes, please.
I do. I think Gloria and Co are still having the challenge. I'm coming. I don't know what to do. Okay, so S is directly proportional to theta. Okay. S is directly proportional to theta. Now, when you watch this closely, the observation is that look at this distance from the center to the position of the object. What is the name given to this distance from the center? What's the name given to it? What's the name given to that distance from the center of the circle?
The radius.
That's the radius. Okay. When you look at it, it's always as if this radius is sweeping a certain angle. When it is moving from A to B, it's as if the radius sweeps a certain angle before. When it is moving from A to B, A to C, it's like the radius of the circle sweeping a certain angle corresponding to it. From A to D, it appears the radius is sweeping a certain angle corresponding to the new position of the object. So we define the angular displacement. The angular displacement theta is defined as the angle which is swept by the radius of the circle at the center. Okay. The angular displacement, angular displacement which we are representing by the letter theta is defined as the angle swept or covered by the radius of the circle, by the radius at the center of the circle. So angular displacement theta is defined as the angle swept or covered by the radius at the center of the circle. And we realize that the linear displacement S is directly proportional to the angular displacement theta. In direct proportionality or in proportionality, when you introduce an equal to sign, there is a constant, okay, theta. And this constant of proportionality is equal to the radius, the constant radius of the circle at whatever position. So S is equal to R theta. And this establishes the relationship between linear displacement within the circumference and angular displacement at the center. Okay. Relation or an equation establishing the relationship between linear displacement and angular displacement. In circular motion, whenever you hear angular quantities or measurement, then it means it occurs at the center of the circle. All angular measurements or quantities occur at the center of the circle. All linear quantities happen at within the circumference. Please, are we okay?
Mr. Jan,
Hello.
isn't as much as in circular motion, the displacement around the circumference is described as linear. It's not necessarily linear. Or should we just take it like that?
It's linear because you see, within the circle, when I consider any 2 points, maybe A to C. Okay, what is distance? Okay, a distance is any interval between 2 points. So we can actually measure this interval between the 2 points. So it's more or less like a linear motion within the circumference. That's why linear. Okay.
Okay, so we do not take into consideration the circular part itself, but just the distance between
distance.
okay.
Yes. Okay, so this is under circular motion and rotational motion, when you hear angular measurement occurs at the center, whereas linear measurement occurs within the circumference. And so there's a relationship between linear motion and linear displacement and angular displacement. The SI unit of angular displacement, don't forget the SI unit of linear displacement and the radius are the meter. Okay, other subunits can also be centimeter, but the SI unit of angular displacement is angular displacement theta is radian, which is shortened as RAD, what you say as rad. Okay, so the SI unit of angular displacement is radian. I think that the problem is sorted a bit. I've seen about 17 or about 16 of you joining. Thank God. I cover a lot of time for the Wi-Fi. Okay. Now other units. Okay, please. I said the radian is the SI unit. Other units can be rev. It can be angular measurements. Other angular measurement can be revolution, angular measurements. Measurements can be in, okay, our usual degree, shortened as dec, and then in revolution, shortened as rev. The SI is radian, but other units can be degree and revolution, just as in distance or measurement of length. SI unit is in meter, but we can have the centimeter and then the millimeter. Are we okay? Are we fine?
Yes, please.
Okay. Now we can convert just as we can convert centimeter, millimeter to meter, we can also convert other units to the SI units. Okay. So we say that 1 revolution, 1 rev, 1 complete revolution. When the body starts from maybe a point A, goes and then come back to the same point, we have 1 complete revolution. Okay. 1 revolution is to 2 pi in radian. 2 pi radian. Okay. So 1 rev is equivalent to 2 pi radian in radian. Then the same 1 rev in degree is equivalent to 360. 360 degree. So these are the conversion equivalents we use. Okay. 1 rev is equal to 2 pi radian, meaning if a body makes 2 complete revolutions, 2 revs, okay, 2 revs will be equal to 2 times 2 pi radian, okay, or 2 times 360 degree. Is that okay? So this is the conversion equivalence. If you want to convert from revolution to degree, revolution to radian, or radian to revolution, and the other way around. What it means, what this means is that a revolution or an angular displacement of 360 degrees will be equivalent to what in radian? Yes. An angular revolution of 360 degrees will be equivalent to what in radian?
2 pi 2 pi radian.
So yes, 2 pi radian. So 360 is to 2 pi radian, or 6.28 radian. This is 6.28 because when you substitute the value of pi and then multiply by 2, check and then confirm the result for me. When you substitute the value of pi, 22/7, and multiply that by 2, what will you have? What did you get?
6.285.
So approximately 6.28 radian. So either in unit in radian, you maintain the multiples of pi or express it as a decimal. So either 2 pi radian or 6.28 radian. Are we okay? Okay, so when a body goes through a revolution of half rev, what will be its equivalence in radian, and what will be its equivalence in degree? So I need the radian equivalence of this and then the degree equivalent. Yes, do that for me. Half a revolution will be equivalent to what in radian and what in degree?
Pi radian.
So this will be equal to pi radian, or pi radian, or 3.142. Okay.
Yes.
That is when we express it in decimal. Then what about the degree equivalent?
One is
So please, the rest of you, are you following? (180 degrees). Yes, thank you. Okay. All right. Then I want you to quickly do this for me. Convert 3/4 pi radian to 1 degree equivalent and 2 to revolution. We are converting 3/4 pi radian to degree and then to revolution. Hey, are you through? Anadubia,
Mr. Dear,
what did you get for the first part? Converting 3 pi radian to degree. What did you get?
Mr. Dear,
Yes.
please, Gloria has joined now.
Okay. So what did you get for 3 pi radian to degree? Yes. Roma, what did you get? Hey, Roma is not here. Okay. Let's do it. So you.
Mr. Dear,
Mr. Dear.
360.
Yes. 60. Okay, let's see. So
Mr.
we
Dear.
know. Hello.
Please, I got 135 degrees.
Okay, so we are doing it. So that you can use that to assess what you've done. Okay. All right. How the quick way of converting this to degree is that I know pi is equal to 180 degrees. So if pi is equal to 180, then in place of pi 3/4 by, I substitute 180 degrees. Okay. 2 goes into 4, 2, and 2 goes into this 90. 2 goes into this 45. So I have 3 by 45 degrees. What is 3 times 45 degrees?
135.
Pardon?
135.
So 135 degrees. Okay. In the same way, assuming I'm given 5/7 pi radian to convert it to degree, I know pi is equivalent to 180 degrees. So 5/7 by 180. Then multiply 5 by 180 and divide by 7. You are there. That's the trick. Okay. So if you got 135, mark yourself correct. If you are somebody Who is a fan of ratio and proportion? Then, you know, 2 pi radian is to 360. So if 2 pi radian is to 360, then 3 pi on 4 radian is to an unknown. So use ratio and proportion. X on 3 pi on 4 will be equal to 360 on 2 pi. Therefore, X will be equal to 360 on 2 pi times 3 pi on 4. This is up to you. So pi, and then you have 360 times 3, all divided by 6. 2. Okay. What did we get for degree? We had 135. We had 135, right?
Yes, please.
So if 2 pi is to 360, then 3 pi on 4, we don't know. We are equating it to x. So x over this must be equal to 360 over 2 pi. Check and then confirm for me. So that will also check, and let's have, because this is giving me, I think 180, which is not right. Check. Let's see what is. Let's see what is wrong.
Please, 60 degrees times the 3.
Okay. All right.
Please, what should we check?
No, I'm saying that when we converted, we got 135. Right.
Okay.
But here it is giving us 180. So confirm. Let's see what is wrong with. Okay, what has happened? X on this is equal to 360 on 2 pi. So when you make x the subject, you have 360 on 2 pi times 3 pi on 4. Okay, the pi will cancel. I'm coming. Let me check again. So the pi will cancel. We have 360 by 3 on 8. Multiply and divide, let's see.
Please, is 60 degrees on
Mr. Dia.
Hello.
Please, I can't see. Okay.
I hope you can see now.
Yes, please.
Mr. Dia.
Hello.
Please, the 3 on 4 pi, the one that we changed to degrees, can't we use that one to find for the one in revolution?
Come again.
And please, I'm asking that. Have you seen the 3 on 4 pi? So should I to change it to degrees first?
Yes.
So after we change, can't we use that one? And we use the equation that says 1 rev is equal to 360 degrees.
Oh, yes. We can also use that.
Okay. Okay.
Mr. Adrian,
Hello.
you wanted us to tell you the answer, but you've written it already.
No, I've confirmed. Okay. So I'm giving you 2 different ways of converting from degree to radian to degree. Either you substitute the pi equivalent or you use ratio and proportion. Okay. Let's look at the second question, converting this to revolution. So 2 pi radian is to 1 rev. Okay, I have 3 on 4 pi radian. That will be unknown. So by ratio and proportion, you can find that. So if, let's assume this is x, it means that x on 3 pi on 4, okay, must be equal to 1 rev on 2 pi. X therefore is equal to 1 rev times 3 pi on 4 divided by 2 pi radian. Okay. This and this will cancel. 3 over 4. So this must be 3 on 8 rev. This must be 3 on 8 rev because you have 3 over 4. The denominator will come and multiply this. And so 3 over 4 pi radian will be equivalent to 3 out of 8 revolution. Please, are we okay?
Mr. Teacher, please, is it advisable to leave it in decimal?
Oh yes, you can also do that. But you see, I'm not expressing it in decimal because when I divide, I have to run. Okay, because I'll have decimal figures, I have to run. That's why I've left it in fraction. Are you okay?
Please, okay.
All right.
Yes, please. Thank you.
We'll be applying this so much. That's why I'm giving you how to look at the conversion. All right. So as the body moves within the circular part, there is a corresponding change. How many? Okay, we have 4 minutes. There will be a certain angle subtended at the center of the circle, angular displacement. Now, in linear motion, whenever you have displacement S, and then the displacement changes with time. A body starts from A, comes to B, moves to C, okay, within equal time interval. Let's assume 1 second. 1 second. So within equal time intervals, its displacement is changing. When there is a change in displacement, delta S on with changing time, dt, we have velocity. So the rate of change of velocity with time generates, the rate of change of displacement with time generates velocity. Now in circular motion, we have a similar thing. The body is at a point A. Its displacement from the center gives us the fixed radius. Now the body's position within equal time interval, the t, comes to B, then within the same time interval, also moves to C, then moves to D. Okay, what's happening? This angle is changing. This angle is θ1. When it moves to C, the angle changes to θ2. When it moves to D, the angle changes to θ3. So within equal time intervals, the angle, because the displacement, the linear displacement, the angular displacement is also changing, okay, it gives us a new parameter. So when there is rate of change of angular displacement with time, dt, with changing time, it also gives us a new quantity we call as angular velocity. Within the circumference, because the linear displacement is changing, S1, from here to here, S2, from here to here, S3. So the linear displacement within the circumference is changing. So it will also amount to linear velocity within the circumference. The changing angle at the center also amount to a changing angle with respect to time, which we call as angular velocity, represented by the letter omega. Please, are you fine? Are you okay?
Cecilia, please, can you repeat it? I don't get it.
Let me come here. Oh, I will have 1 minute to go on our commercial break and then we're going.